The fastest object human beings have ever launched has been flying without stopping for 49 years, and it has covered 1/365th of a light year. NASA has calculated the second it finishes that fraction, 2 in the morning, Pacific time, on the 18th of November, 2026, when Voyager 1 becomes the first thing we have built to sit one light day from Earth. At that rate, the whole light year takes about 17,600 years, 3 times all of recorded history, to cross the smallest unit on the map. And it is not a crossing through nothing. A cube of that empty space, 1 light year on a side, holds 70 times the mass of the Earth in hydrogen, and every atom of it becomes ammunition the moment you hurry. The star you aimed at moves 8.5 light years while you move 1. By the end of tonight, you will know why 6 unrelated parts of physics all fail at the same range, and the one thing nobody mentions, which is where you are actually standing when you arrive. Get comfortable. If you enjoy having the size of things quietly taken apart on you, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this, the nearest star will feel much further away and a great deal closer at once. Now, let's gently drift into this. Somewhere near you, probably in a cupboard you could reach without getting up, there is a dinner plate. An ordinary one. About 25 centimeters across, white or nearly white, the kind you would put a meal on without thinking about it. I want you to keep that plate in mind for the next few minutes, because it is going to do something that no photograph and no documentary has ever quite managed to do for me, and it is going to do it using nothing but its own width. Imagine it set down on a table in front of you. Now imagine that the rim of that plate is the orbit of Neptune. Not a diagram of Neptune's orbit. The orbit itself, shrunk down until the entire outer edge of the planetary solar system fits inside a circle the width of your 2 hands. At that scale, the Sun is a speck at the center, smaller than a grain of salt. The Earth is about 4 millimeters out from it, the thickness of a pencil, roughly, or the width of the little fingernail on a child's hand. Everything you have ever seen a photograph of is inside that 4-millimeter gap or just beyond it. Every sunrise, every ocean, every city, every person who has ever lived. Mars is a little further along. Jupiter sits about halfway to the rim. Saturn a bit past that. Uranus and Neptune finish the job at the edge of the porcelain. And inside that plate is everything human beings have ever touched. Every spacecraft, every probe, every photograph taken from a camera we built. The whole of the space program, every launch since 1957, every mission that has ever left the ground, all of it happening inside a white circle 25 centimeters across, on a table, in a room. There is one exception, and it is worth placing carefully, because it is the only thing we own that has ever left the porcelain. The most distant object human beings have ever built is a spacecraft called Voyager 1, launched in 1977, still flying. On the scale of that plate, Voyager 1 is about 70 centimeters from the center. Off the plate, off the placemat, out past the edge of the table setting, roughly an arm's length away from the rim of the solar system. 49 years of continuous flight, and on our kitchen table model, it has traveled about the length of your forearm. Hold that image. We will come back to it, and it is going to get much stranger. Now stand up. Take the plate with you if you like, but leave it on the table when you get to the door, because you are going to need to walk away from it. Go out of the room. Go down the hallway, out the front door, onto the street. Turn in whatever direction has the longest clear run and start walking. Past the parked cars, past the neighbors' houses, the ones you know and the ones you have never spoken to. Past the corner. Keep going. Past the second corner, past the shop, past whatever landmark you use when you give someone directions to your own home. Keep walking until you have covered about 260 meters, 2.5 football pitches, laid end to end, and then stop and turn around and look back the way you came. At the building you cannot see into anymore. At the room you cannot see. At the table you cannot see. And at the plate on it that you certainly cannot see. That is 1 light year. Not 4. Not the distance to the nearest star. 1. The single smallest unit anyone uses when they talk about how far apart the stars are. The unit that gets chosen precisely because it is supposed to be the friendly one, the manageable one, the one that lets a person nod along. And between the plate and where you are standing there is nothing. Not a smaller plate. Not a marker. Not a halfway point. 260 meters of ordinary street, and every single centimeter of it is space that no human being will ever cross. Here is the number itself, and it is worth hearing in full at least once, because almost nobody ever says it in full. 1 light year is 9 quadrillion, 460 trillion, 730 billion, 472,580,800 meters. That is not an estimate. That is not a figure rounded off for convenience or updated as instruments improve. That is exact to the last meter, and it will not change. The reason it is exact is a small and lovely piece of bureaucratic history. Since 1983, the speed of light has not been a measured quantity at all. It is a defined one. 299,792,458 meters per second, by international agreement exactly, with no error bar. We stopped measuring it and started using it as the ruler. The meter is now defined in terms of the speed of light, rather than the other way around. So when you take that defined speed and multiply it by a defined year, 365.25 days, the astronomer's year, chosen for bookkeeping neatness, you get a distance with no uncertainty in it anywhere. 9 quadrillion, 460 trillion meters and change. Roughly 9.5 trillion kilometers. Roughly 5.88 trillion miles. And here is the conversion that starts all the trouble, the one I would like you to carry with you through the rest of tonight. 1 light year is 63,241 astronomical units. An astronomical unit is the distance from the Earth to the Sun. 149.6 million kilometers. 8 minutes and 20 seconds at the speed of light, which is to say, when you look at the Sun, you are looking at where it was 8 minutes ago, and if it went out, you would have those 8 minutes before anyone noticed. That gap is already past what a human mind can hold. Nobody has any intuition for 150 million kilometers. We know the words. We do not know the thing. And a light year is 63,000 of them, laid end to end. Not 63. Not 630. 63,241 Earth to Sun distances, in a row, in a straight line, with nothing in between them. If you spent 1 second on each 1 second per Earth to Sun distance, no pausing, no sleeping, you would be counting for 17.5 hours before you finished. And at the end of it, you would have counted out the smallest unit of interstellar distance there is. Try it another way. If you got up right now and started walking at a comfortable pace, 5 kilometers an hour, and you never stopped, never slept, never ate, never turned around, walked straight through oceans and mountains as though they were not there, you would need about 216 million years to cover 1 light year. 216 million. The first dinosaurs appeared around 230 million years ago. You would need to have set off before them, and to still be walking now, and to have covered the distance only once. Put yourself on a commercial airliner instead, at 900 kilometers an hour, cruising forever. 1.2 million years. Modern humans have existed for about 300,000. You would need to have boarded 4 times before our species existed. And light, the fastest thing there is, the thing nothing in the universe has ever outrun, the thing that crosses the entire gap between the Earth and the Sun in the time it takes you to walk to the kitchen light, takes 1 year. That is not a coincidence or an approximation. That is the definition. The unit is built out of light's own performance over 1 trip around the Sun. It is the best possible time. It is the record, held forever, by the only thing capable of holding it. It is worth noticing, in passing, that we do have units built out of light that behave themselves perfectly well. A light minute, a light hour, a light day. Nobody has any trouble with those. The Sun is 8.3 light minutes away, and that feels correct. It feels like a distance you could describe to somebody over a phone call. Neptune is about 4 light hours out. The entire solar system, from the Sun to the outermost planet, is under 9 light hours across, which means that if you left the Sun at the speed of light after breakfast, you would pass Neptune before bed. Those units work. They sit in the mind without struggling. And then you multiply by 365 and something breaks, and the unit that was helpful becomes a unit that hides. So already, before anything else, before we have talked about engines or fuel or the physics of what happens to a ship at speed, there is something quietly wrong with the picture most of us carry. We tend to imagine interstellar distance as a very long road. A road is a thing with a beginning and an end, and, crucially, a middle. Landmarks, milestones, a service station somewhere around the halfway point. Something to measure yourself against. 9.5 trillion kilometers, and not one landmark in it. There is nothing at the halfway point of a light year. There is nothing at any point of a light year. It is not a road between 2 places. It is a measurement taken inside an absence, and we have given it a comfortable name and a friendly-sounding unit, and passed it around as though it were a number like any other. Which raises a question I did not expect to find interesting when I started looking into this, and which turns out to be the first real crack in the whole thing. Why does the smallest unit of interstellar distance have a name that sounds like a length of time? Who decided that? And what, exactly, were they trying to make us feel? In a cold observatory in Königsberg, in the autumn of 1838, a man is looking at the same faint star for the 100th time and writing down an angle. The man is Friedrich Bessel. The star is a dim, unremarkable double in the constellation of the Swan, catalogued as 61 Cygni, and he has chosen it for one reason only. It moves. Not much, and not quickly, but faster across the sky than almost anything else anyone has catalogued, and Bessel has reasoned correctly that a star which appears to move quickly is probably a star which is close. The instrument he is using is called a heliometer, and it works by splitting the lens in half and sliding the 2 halves against each other until 2 images of the sky line up, which lets him measure angles smaller than anyone had reliably measured before. The angle he is chasing is called parallax, and it is the simplest idea in astronomy. Hold up a finger at arm's length and close one eye, then the other. The finger jumps against the background. Move your head further apart, and the jump gets bigger. The Earth does this once a year, swinging from one side of its orbit to the other, 300 million kilometers of baseline, and if the stars are at any finite distance at all, then they must jump too. For 2 centuries, nobody could see the jump. And that absence was the single most powerful argument against the idea that the Earth moves at all. When Copernicus proposed that the Earth goes around the Sun, the strongest objection was not religious, and it was not stubborn. It was observational. If we are swinging back and forth across 300 million kilometers of space every year, the stars should visibly shift, and they do not. Astronomers looked and found nothing, year after year, generation after generation. It was one of the great embarrassments of the science. It turned out they were finding nothing for the only reason that mattered. The stars do shift. The shift was simply smaller than any instrument on Earth could see, and it was smaller because the stars were further away than anybody had been willing to believe. Bessel measured it. The angle came out at about 3/10 of a second of arc. To put that in something you can hold, a second of arc is 1/3600th of a degree. 3/10 of that is roughly the width of a human hair seen from 12 meters away. It is about the apparent size of a golf ball sitting on the surface of the moon. That is the wobble. That is the entire signal teased out of a photographic plate-free, computer-free, electricity-free observatory by a man sliding 2 halves of a lens against each other in the dark. And from that angle, he got a distance, about 660,000 times the radius of the Earth's orbit. The first distance to a star ever measured by a human being. He was, we now know, within about 10%. The modern figure for 61 Cygni is a little over 11 light-years, which for a first attempt at the hardest measurement in the history of the subject is remarkable. He was not alone for long. Within roughly a year, Thomas Henderson published a parallax for Alpha Centauri, taken years earlier from the Cape of Good Hope and sat on, out of caution, and Friedrich Struve published one for Vega. After 200 years of failure, the first 3 stellar distances in history arrived almost together. Now, here is the part I find quietly telling. Bessel, having produced the number, remarked that light would take about 10 years to make the crossing. He said it the way you might mention that a drive takes 3 hours. It was a translation offered for the reader's benefit, not a unit, and by several accounts he had no interest in turning it into one. He had spent his career fighting to make astronomy a science of measured quantities. A distance is a distance. Dressing it up as a duration was, to him, not obviously an improvement. The dressing up happened anyway, 13 years later, and it did not happen in a research paper. In 1851, a German science writer named Otto Uhle published a popular astronomy article with a title that translates roughly as "What We Read in the Stars." Uhle was not an observer. He was a popularizer, in the honorable sense a man whose job was to take what the astronomers had found and hand it to people who would never look through a telescope. And in that article, for the first time in print, the word appears, Lichtjahr, light year. He knew immediately that it was odd. He knew a reader was going to stop at the word year in the middle of a sentence about distance and object. So he answered the objection in the piece itself, on the day the unit was born, and his defense was that German already had a perfectly ordinary word for a distance measured in time, the Wegstunde, the walking hour, the distance you cover in an hour on foot. Nobody complains about that. Why complain about this? It is a good argument. It is also the exact moment the disguise went on. Because a walking hour and a light year are not the same kind of thing at all. A walking hour is a distance you can walk. That is the whole point of the unit. It is scaled to the person using it. It tells you not just how far, but how much of your day it will cost, and both halves of that are useful to you. A light year tells you how much of the day it will cost light. It is calibrated to something you are not and can never be. The friendliness of the word is entirely borrowed. It sounds like a measure of your effort, and it is a measure of the universe's best possible effort, which is a different quantity entirely. Say it plainly, and it stops being comforting. The light year is not really a distance at all. It is a rate wearing the clothes of a distance. And the professionals, tellingly, never took to it. Open almost any research paper in astronomy and you will not find light years. You will find parsecs, a unit that falls directly out of the parallax measurement Bessel was making, defined as the distance at which one Earth-Sun radius would subtend 1 second of arc. It is bigger and it is uglier, and it has no comforting word buried in it. 1 parsec is 3.26 light years. There is no star that close. The nearest, Proxima Centauri, sits at about 1 1/3 parsecs. So the situation is this. The scientists measuring these distances use a unit that sounds like nothing. The unit the rest of us were given was invented for a magazine article, defended on the grounds that it feels familiar, and has been quietly doing that job ever since, smoothing off the edges of a number so that a general reader can nod and move on. Even the year inside it is a convenience. It is not the year you live in, the tropical year of 365.2422 days tied to the seasons. It is the Julian year, 365 1/4 days flat, chosen because it makes the arithmetic clean. The difference between the two sounds trivial and comes to about 600 million kilometers, which is to say, the rounding error in the definition of a light year is 4 times the distance from here to the sun. That is the shape of the thing. Every single simplification in the way we talk about this makes the number smaller in the mind, and every one of them is larger than the entire world we live in. So we have a unit designed for comfort, sitting on top of a quantity that has never been comfortable. The obvious next question is the practical one, the one anybody would ask second. Fine, it is enormous, but how long would it actually take? Not for light. For us. For the fastest thing we have ever managed to build and throw. That number exists. It is not a guess, and it is not a projection. There is an object out there right now, made by human hands, that lets us calculate it exactly, and in 3 months' time, it is going to reach a milestone that will let us calculate it to the second. There is a machine out in the dark tonight, about the size of a small car, with a golden record bolted to its side, and a dish antenna pointed back the way it came, and it is the reason we do not have to guess at any of this. Voyager 1 left the ground on the 5th of September, 1977. It has not stopped since. It has not slowed down in any meaningful way, because there is almost nothing out there to slow it down, no air, no friction, nothing but the sun's grip weakening behind it. It is moving at about 17 kilometers per second, which is roughly 61,000 kilometers an hour, about 38,000 miles an hour. Every second while you are lying here, it puts another 17 kilometers between itself and everything it came from. On the 18th of November, 2026, at 16 minutes and 7 seconds past 2 in the morning Pacific time, Voyager 1 will be exactly 1 light day from Earth. That is not a rounded figure. NASA has calculated the moment to the second. 16 billion, 94 million, 799,096 miles. About 25.9 billion kilometers. 173 astronomical units. And it will be the first object that human beings have ever made to get that far. Picture the moment, because it is worth sitting inside. It is the middle of the night on the west coast of the United States. The spacecraft is somewhere far above the plane of the planets, in a part of the sky nothing has ever occupied before. It is running on a plutonium power source that loses about 4 watts of output every year, so instruments have been switched off, one at a time since the 1990s, to keep the essential ones alive. Its radio transmitter puts out about 23 watts, which is less than the bulb in a refrigerator. Its onboard memory totals somewhere around 70 kilobytes less than a single photograph on the phone next to your bed. And at that exact second, nothing happens. There is no boundary there. No instrument on board registers anything. No light changes, no signal chirps, nothing crosses a line, because there is no line. The spacecraft does not know. It has been doing precisely the same thing for 49 years, and it goes on doing precisely the same thing through the moment and out the other side. The only thing in the universe that marks the event is a number in a table on Earth, calculated in advance by people who will be asleep when it happens. 1 light day. After 49 years and 2 months of unbroken flight. Launched before most of the people listening to this were born. Launched when the fastest computer on Earth was slower than a modern doorbell, and still going, still reporting, still moving at 17 kilometers a second. And what it has covered, in all that time, is the distance light covers between one bedtime and the next. Now do the multiplication, because it is the whole of this part of the video. A light year contains 365¼ light days. At its current speed, Voyager 1 would need somewhere in the region of 17.5 to 18,000 years to cross 1 light year. Take the speed and the distance directly, and you get about 17,600 years. That is the number. That is the real, measured, no assumptions required answer to the question of how long it takes the fastest thing humanity has ever launched to cover the smallest unit of interstellar distance. Set that against something. Human civilization, counted generously from the first cities in Mesopotamia, is about 6,000 years old. Writing is a little younger. Everything you have ever heard of, every empire, every language, every war, every book, every piece of music, fits inside 6,000 years. Voyager 1 would need to fly for nearly 3 times that span, continuously, without a fault, without a course correction, without anybody left to listen to it, to complete the first light year. And I want to be careful here, because there is an easy way to hear that number and file it as merely large. It is not merely large. It is a specific kind of large. It is the kind where the machine outlasts the civilization that built it by a factor of 3 and still has not arrived. There is one more thing about Voyager, one that belongs here, and I am going to plant it now and leave it, because it becomes important much later tonight. In August of 2012, at about 121 astronomical units from the Sun, Voyager 1 crossed something called the heliopause. Voyager 2 crossed it 6 years later, in November of 2018, at about 119. The heliopause is the surface where the Sun's outward wind of charged particles finally runs out of push and is stopped by the thin gas of the surrounding galaxy. When it happened, the headlines said that Voyager had left the solar system, and, in one sense, that was true, and, in another sense, it was one of the most misleading sentences ever printed about space. Because leaving the Sun's wind is not the same thing as leaving the Sun. The wind stops at 120 astronomical units. The gravity does not. And we will come back to exactly where the gravity does stop at the end of tonight, because it is the answer to the question in the title, and it is not where anybody expects. Meanwhile, the conversation is already breaking down. At 1 light day out, a command sent from Earth takes 24 hours to arrive, and the answer takes 24 hours to come home. An engineer who says good morning to Voyager on a Monday gets the reply on Wednesday. That is, at one light day. Multiply that gap by 365 and hold on to what it does to the idea of a conversation, because we are going to come back to it. Now, Voyager 1 is not the speed record, and it is important to be fair to the engineering. The record belongs to something else entirely. The Parker Solar Probe was built to fly into the Sun's outer atmosphere, and to do it, it has spent years using close passes of Venus to bleed off orbital energy and tighten its loop. On the 6th of November, 2024, it made one such pass. 7 weeks later, on the 24th of December, 2024, at 53 minutes and 48 seconds past 11 in the morning, Universal Time, it fell through its closest approach to the Sun, about 6.17 million kilometers above the visible surface, which is close enough to be inside the corona. And as it did so, it reached 192.22 kilometers per second. That is 692,000 kilometers an hour, about 430,000 miles an hour. It is the fastest any object made by human beings has ever moved, and it repeated the feat on the 22nd of March, 2025. In terms of light, it is 0.064% of the speed of light, not 6%. Not 0.6. 0.06% At that speed, 1 light year takes about 1,560 years. That is 11 times better than Voyager, and it is still longer than the time since the fall of the Roman Empire. A ship launched at Parker's record speed on the day Rome fell would not have arrived yet. But there is a caveat here that I am not willing to skip past, because the number is often quoted as though it were a cruising speed, and it is nothing of the kind. Parker is not traveling at 192 kilometers per second. Parker is falling at 192 kilometers per second. It is in orbit around the Sun, at the bottom of the deepest gravity well in the solar system, and every meter per second of that speed is borrowed from the Sun and paid back on the way out. It is a speedometer reading taken at the bottom of a hill. There is no engine involved. Nothing has ever sustained that velocity, and there is no configuration of anything we currently know how to build that turns it into a sustained one. To leave with that speed and keep it, you would need to generate it yourself, in the flat, against nothing, and that is a different problem by an enormous margin. The rest of the ladder is worth laying out, because what is remarkable is how little the rungs matter. New Horizons left Earth faster than anything before it, about 58,500 kilometers an hour at launch in January 2006, on its way to Pluto. Today it is doing around 16.3 kilometers per second, which is slower than Voyager 1, because the Sun has been quietly pulling on it for 20 years and taking the speed back. The fastest any human being has ever traveled is about 39,900 kilometers an hour, set by the crew of Apollo 10 coming home from the Moon in May of 1969. That record is now well over half a century old, and nobody has come near it since. An airliner, 1.2 million years. A person walking, 216 million years. Look at the spread there. From a walking pace to the fastest object ever built is a factor of about 140,000 in speed. 4.5 orders of magnitude of human effort, from a stroll to a spacecraft falling into the Sun. And the answers come out at 200 million years, 1 million years, 18,000 years, and 1,500 years. Not one of them is a journey. Not one of them is even in the neighborhood of a journey. The best answer available, the actual, physical, verified best, is that our fastest machine, at a speed it cannot sustain, would take longer than recorded history to cross the smallest unit on the map. So in one sense, we already have the answer. It never ends. If by never you mean within any timescale, a person or a culture or a species can plan around. 1,500 years is longer than any institution has ever survived. 18,000 is longer than agriculture. And yet, if you are the kind of person who does not let a thing go, that is not really an answer, is it? It is a description. It tells you that it is slow. It does not tell you why we cannot simply build a better engine and go faster, the way we have with every other form of travel human beings have ever attempted. Ships got faster. Trains got faster. Aircraft got faster, until they got so fast that we stopped bothering. Why does this particular curve refuse to bend? The answer is not about engineering. It is about arithmetic, and it is the most quietly brutal piece of arithmetic in this entire subject. Think about a car on a wet road, and the moment the driver puts their foot on the brake. At 30 miles an hour, that car stops in a certain distance. At 60 twice the speed, most people's instinct says it will take twice as far. It does not. It takes 4 times as far. Every driving instructor in the world has to teach this, and every learner has to be told twice, because the intuition is so strong and so wrong. Double the speed, quadruple the stopping distance, triple the speed, and you need 9 times the room. That is not a fact about cars, or about tires, or about wet roads. It is a fact about motion itself, and it is the reason a light year cannot be crossed. The energy carried by a moving object does not rise in step with its speed. It rises with the square of its speed. Go twice as fast, and you are carrying 4 times the energy. Go 10 times as fast, and you are carrying 100 times the energy. Every time you want to halve a journey, the universe hands you a bill that is 4 times larger than the one you just paid. And it does this at every scale, from a bicycle to a starship, without exception and without appeal. Now apply that to the distance we have been circling. Suppose you decide that 17,000 years is unacceptable, and you want to cross 1 light year in 1,000 years instead. That is still a hopeless timescale. 1,000 years ago there was no such thing as England as we know it, but it is 17 times better than Voyager. To do it, you need to be moving at about 300 kilometers a second, permanently, in the flat, with no sun to fall towards. And to give 1 single kilogram of your ship, that speed costs somewhere in the region of 45 billion joules. 45 billion joules is roughly the energy in a ton of TNT. For 1 kilogram. For a bag of sugar. Your ship has a hull and instruments and a power supply and shielding, and if there are people aboard, water and air and food and everything that keeps them alive, and every single kilogram of it is a ton of high explosive delivered as forward motion, and then that ship arrives in 1,000 years. Now say 1,000 years is still too long. You want a century. 1 human lifetime, plus a bit long enough that a person born at launch might have a great-grandchild who sees the arrival. For that, you need 1% of the speed of light, 3,000 kilometers a second, and the cost per kilogram has gone up by a factor of 100. Push once more. 10 years, an actual journey. A thing a crew could survive. A thing a space agency could plan. That requires 10% of the speed of light. And now the cost per kilogram is around 450 trillion joules, which is about 100 kilotons of TNT. Per kilogram. Hold that against something real. The bomb dropped on Hiroshima released about 15 kilotons. So we are talking about roughly 6 or 7 Hiroshimas, converted perfectly and without waste into forward motion for every kilogram of the vehicle. For the kettle in the galley. For a spare bolt. For the cat, if you brought one. And here is the part that turns the arithmetic from difficult into cruel. All of that buys the acceleration only. It gets you up to speed. It does not slow you down at the other end. Stopping costs the same again. You have to shed exactly the energy you spent, and there is nothing out there to push against. No air, no ground, no friction, nothing. So either you carry a second, equal fortune in fuel to burn on arrival, or you do not stop, and your 10-year journey ends with the ship crossing the target system in a matter of hours and continuing forever into the dark on the other side. This is what a real wall looks like, and it is worth being precise about why it is different from every other barrier in the history of human travel. Every previous limit was a limit of technique. The oceans were impassable until someone worked out how to sail against the wind and how to know where they were. The sky was impassable until someone found a wing shape that worked. The sound barrier, which was seriously discussed as a physical impossibility, a place where aircraft would simply come apart, turned out to be a matter of getting the shape and the control surfaces right. In every one of those cases, the barrier fell to cleverness. Somebody thought of something, and then the thing that could not be done was routine within a generation. This is not that. This is arithmetic sitting in the road. There is no shape you can find, no material you can invent, no configuration of anything that changes the relationship between speed and energy. It is not a property of your engine. It is a property of moving. And its shape is the cruelest possible shape for a species that improves by trying harder, because the cost goes as the square. Improving your engine by a factor of 10 buys you a little over 3 times the speed. Get 100 times better, and you go 10 times faster. Get 1,000 times better, 1,000 times better than the best rocket ever built, which is a fantasy on any timescale you like, and you are 10 times faster still, and 1 light year is down from 17,000 years to 550. That is what makes this different from a wall, and I want to give you the right word for it, because the right word changes how the whole rest of tonight feels. It is not a wall. A wall is a thing you get past when you find the door. This is a receipt. The price is printed, the arithmetic is public, nobody is hiding anything, and every improvement you make is honestly credited to your account, and it is simply never enough, because the price rises faster than your ability to pay it. There is no cleverness that gets around a receipt. You can only pay it or not pay it. And I think that is the quiet thing underneath this whole subject, the thing that makes it sit differently from other hard problems. We are used to limits that are waiting for us to grow up. We tell ourselves that story constantly, and for most of history it has been true. The thing that could not be done in 1 century became ordinary in the next, and the people who said it was impossible were remembered mostly for having said so. That story has trained us to treat every barrier as temporary and every doubter as unimaginative. But some limits are not waiting for anybody. Some of them are simply the shape of the world, printed clearly, in advance, in a form anyone can check. The uncomfortable part is not that this one is hard. It is that it is not hiding. And there is a second, quieter clause on the same receipt, which I will mention briefly because it deserves a whole video of its own, and this is not that video. The energy has to come from somewhere. If you carry your fuel the way every rocket ever built has carried its fuel, then the fuel has weight, and the weight has to be accelerated too, which needs more fuel, which has more weight. The requirement does not add up. It compounds. And it compounds so aggressively that a conventional chemical rocket, asked to reach even 1% of the speed of light, requires a fuel-to-ship ratio with hundreds of digits in it, more fuel than there are atoms, available to make fuel out of. This is why nobody serious proposes chemical rockets for this. It is not a matter of scale. There is no scale. The obvious answer to that is to carry a better fuel, something that gives more energy per kilogram so that you need fewer kilograms. And the ladder of available fuels is real, and it is short. Burning chemicals, which is what every rocket that has ever flown does, converts something like 1/10,000,000th of the fuel's mass into energy. Splitting heavy atoms fission gets you to about 1/10 of 1%. Fusing light ones, which we have not yet managed to do usefully anywhere outside a weapon or a star, gets you to somewhere near half of 1%. And then the ladder simply stops with one rung left on it, antimatter, which converts 100% of its mass into energy, perfectly, with nothing left over. That last rung is the one that makes the arithmetic work, and it is the reason antimatter turns up in every serious conversation about this. It is also the reason the conversation ends there, because the total quantity of antimatter human beings have ever produced, added together across every laboratory and every decade, amounts to a few billionths of a gram, and making it consumed vastly more energy than it could ever give back. Antimatter is not a fuel. It is a battery with terrible efficiency and a manufacturing rate measured in atoms. So the ladder of fuels does not rescue the receipt. It just tells you, with some precision, exactly how far short of it we are. So there we are. Not slow because we have not tried. Not slow because the engines are primitive. Slow because the cost of not being slow rises as the square of the improvement forever, and because carrying the means to pay it makes the bill worse. I said earlier that the numbers in this subject have a habit of arriving in a certain order. First the size, then the time, then the cost. And usually, at about this point, somebody who knows a little physics puts their hand up, and they are right to, because there is one thing I have not mentioned. Everything I have just told you assumes that a light year is a fixed distance that stays the same length no matter how fast you go. It is not. And that is not a technicality or a piece of hand-waving. It is one of the best established results in all of physics. It has been confirmed by direct measurement over and over again, and it says that for anyone actually making the crossing, the light year genuinely gets shorter. Physics, in other words, is offering us a discount. A real one. I want to look very carefully at where that discount starts. Imagine a ruler bolted to the side of a ship, pointing forward in the direction of travel, with the destination somewhere off the end of it. For the crew on board, that ruler is the honest measure of how far they have to go. And the extraordinary, well-tested, thoroughly boring to physicists fact is that as the ship speeds up, the distance measured along that ruler genuinely shrinks. Not appears to shrink. Not seems shorter because of some trick of perception or some quirk of light arriving late. The gap in front of them is actually shorter, in their frame, in the only sense of actual that has ever meant anything in physics. This channel has spent a whole night on that idea before, so I am not going to rebuild it from the ground up here. What matters tonight is one thing only. Not whether the discount is real. It is. But where it starts. And it starts appallingly late. At 10% of the speed of light, 30,000 kilometers a second, a speed we have never come remotely close to, a speed that costs 100 kilotons of high explosive per kilogram to reach the light year in front of you, shrinks by about 0.5%. In practical terms, a journey of 1 light year becomes a journey of 1 light year minus about 4.5 days. After all that, after the receipt from the last part has been paid in full, the universe knocks 4 days off a 10-year trip and calls it generosity. At half the speed of light, the shrinkage is about 15%. Better, and still not the thing you would design a mission around. The gap does not actually halve. The light year does not become half a light year for the people crossing it, until you reach roughly 87% of the speed of light. That is the first point where the discount becomes worth talking about, and it is very deep inside the wall we spent the last part building. To give a single kilogram that speed costs something in the region of 20 megatons of TNT equivalent. Not kilotons. Megatons. That is a large hydrogen bomb per kilogram, delivered as forward motion, and it halves your journey. And past that point, the curve does something almost taunting. Because now, at last, it starts to pay properly. At 99% of light speed, the light year has shrunk by a factor of about 7.5 years of ship time. At 99.9%, it has shrunk by a factor of over 20. To compress a light year down into something like a single week aboard, which would make interstellar travel genuinely comfortable, you would need to be moving at 99.981% of the speed of light. So the shape of the offer is this. The discount exists. It is real, it is generous, and at the far end it is spectacular. A ship moving fast enough would cross a light year in an afternoon by its own clocks. And it is arranged so that the region where it starts to help is exactly the region that the previous part showed us we cannot enter. The relief begins on the other side of the wall. There is something almost architectural about that, and I have never quite been able to decide whether it is a joke or a mercy. Physics does not simply refuse. It shows you the door, unlocks it, explains carefully how it works, and prices the handle above the value of the house. 2 footnotes, and then we move on, because I want to be honest about the edges. The first is that even at the fastest speeds anyone has seriously proposed for a real mission, this whole discussion is academic. The most credible interstellar concept anyone has put on paper aims for about 20% of the speed of light, for a payload weighing a few grams. At 20%, the shrinkage is around 2%. 2%. On a 5-year crossing that is a little over a month, every actual, funded, engineering-grade proposal in existence sits in the part of the curve where relativity does nothing for you at all. The relief is not merely out of reach. It is out of reach of the things we are actually trying to build. The second footnote is the one that quietly matters more. The discount is only ever offered to the traveler. Nobody else gets it. The light year does not shrink for the people at home, or for the people at the destination, or for the universe in general. It shrinks only along the ruler bolted to a ship that is already moving impossibly fast. From the outside, from Earth, the crossing takes the time it takes, which is at absolute minimum 1 year, and in practice, a great deal longer. So even in the fantasy where a crew crosses in an afternoon and steps out barely older, they step out into a place where the calendar has moved on without them, permanently, and there is no version of the trip where anyone gets both. And there is a third thing, which is not really a footnote so much as a locked door at the end of the corridor. You might reasonably ask where the curve ends, whether, if you kept pushing, the light year would eventually shrink to nothing and the crossing become instant. The answer is that the curve has no end. It rises without limit as you approach the speed of light, and it never arrives, because arriving would require infinite energy for anything with any mass at all. There is no setting on the dial marked light speed for a ship. The numbers do not merely become large there, they stop being numbers. So, the discount has no floor and no bottom step. It simply gets steeper forever, in a region nobody can enter, for a destination nobody can reach. There is one more consequence of the discount that almost nobody mentions, and it is going to matter in about 10 minutes. If going fast makes the light year shorter in front of you, it also makes everything in that light year arrive sooner, harder, and closer together. The gap does not empty itself out to accommodate you. It compresses, along with everything it contains. Every atom in the way still has to be got past, and now they are all coming at once. That is worth sitting with for a moment before we go on. The only genuine relief physics offers on this problem is a relief that cannot be shared. It is not a shortcut through the distance. It is a private one, taken alone, paid for at a rate nobody can afford, and it leaves everything you departed from exactly as far away in time as it ever was in space. So we have the size. We have the cost. We have the one exemption and the reason it does not apply. What we have not looked at yet is the thing itself. All of this has treated a light year as a quantity, a number on a page, a gap to be crossed, an abstraction with a price tag on it. But a ship crossing it is not crossing an abstraction. It is passing through something, continuously, for the entire journey. And when you actually go and measure what is out there, in the space between the stars, the answer does something I genuinely did not expect the first time I worked it through. It inverts. Twice. Hold your hands out in front of you, about 1 meter apart, and imagine a cube of that size hanging in the air between them. An ordinary cube, 1 meter on each side, roughly the size of a large suitcase or a small washing machine. Now imagine that what is inside it is not the air of your room, but a cube of interstellar space, scooped up from somewhere out along the route we have been discussing and set down in front of you without spilling. What is in there? Somewhere in the region of 300,000 hydrogen atoms. Say it, and it sounds like a crowd. 300,000 of anything sounds like a stadium. But spread 300,000 atoms through a cube, 1 meter on a side, and you have something so close to nothing that the word vacuum barely does it justice. The air in your room, in that same cube, contains something like 25,000 billion molecules. The difference between the two is not a difference of degree. It is a difference of category. And here is the comparison that puts a flaw under it. The best vacuum human beings have ever created, the ultra-clean chambers built for the most delicate physics experiments in the world, pumped down for weeks, sealed, baked, monitored, still contains something in the region of 10,000 particles per cubic centimeter. The interstellar space just outside our own front door is around 0.3 of 1 particle per cubic centimeter, which means the emptiest place ever manufactured on Earth, the product of enormous effort and expense, is roughly 30,000 times more crowded than ordinary space between the stars. We have never made anything as empty as the space we would be flying through. Not close. Not in the same league. The gas immediately around the Sun has a name. It is called the local interstellar cloud, a wisp of hydrogen roughly 30 light-years across that the solar system happens to be inside at the moment. Its density is about 0.3 of an atom per cubic centimeter, and its temperature is around 7,000 degrees hotter than the surface of the Sun. That number always stops people, so let me deal with it. You could stand in that gas at 7,000 degrees and freeze to death. Temperature and heat are not the same thing, and this is one of the few places in the universe where the difference becomes obvious enough to feel. Temperature is how fast the individual particles are moving. Heat is how much energy they can actually deliver to you, which depends on how many of them there are. In the local interstellar cloud, the individual atoms are moving very fast indeed, and there are so few of them that in a whole day of standing there, you would be struck by a number too small to matter. The gas is hot in the way that a single spark from a bonfire is hot, genuinely, measurably, and completely harmlessly. Around that cloud is something larger, and stranger, and emptier still. The local bubble is a cavity in the galaxy roughly 1,000 light-years across, hollowed out by a series of supernovae that went off millions of years ago and pushed the gas outwards, leaving a hole. Its density is around 5/100ths of an atom per cubic centimeter, about 6 times emptier again. The solar system drifted into this region something like 5 million years ago and has been traveling through it ever since. We happen, at this moment in the history of the galaxy, to live in one of the emptiest neighborhoods available. It is worth saying what the gas is, because it is not exotic. About 9 atoms in every 10 are hydrogen, the simplest thing there is. 1 proton, sometimes 1 electron, the first element, and still by far the most common. Most of the rest is helium. And then, in traces so small, they barely register as a rounding error. Everything else, carbon, oxygen, nitrogen, iron, the whole periodic table, every atom of it manufactured inside a star that has already died. Roughly 1% of the mass out there is not gas at all, but dust, solid grains, most of them smaller than a wavelength of visible light, about 1/10 of a micron across, sooty and silicate and irregular. That dust is why distant stars in the plane of the galaxy look redder than they should. It filters the blue out of their light on the way to us, the way a hazy sky reddens a sunset. And the other thing worth saying is how we know any of this, because nobody has ever gone and taken a sample. Almost everything in the last few paragraphs was measured by watching starlight pass through the gas on its way here. The atoms in the way absorb very specific colors out of that light, leaving thin, dark gaps in the spectrum. And from the position and depth of those gaps, you can read off what the gas is made of, how much of it there is, how fast it is moving, and how hot it is. We have weighed the space between the stars using the shadows it casts in other people's light. There is one exception, and it is a lovely one. The solar system is moving through the local interstellar cloud, which means the cloud is blowing through us, and neutral helium atoms, too aloof to be deflected by the sun's magnetic field, sail straight in and can be caught by spacecraft. There is an interstellar wind coming into the solar system from roughly the direction of the constellation Ophiuchus at about 26 kilometers a second, and it has been directly sampled. The space between the stars is not a place we have visited. It is a place that visits us, constantly, at a rate of a few atoms. So that is the medium. Now let us do something with it, because there are 2 ways to add up a light year of that gas, and they give answers that feel like they cannot both be true. The first way is to take a column. Imagine a tube, 1 square meter across the width of a doorway, roughly running straight out from here for a full light year. 9.5 trillion kilometers of tube. Count every atom inside it and weigh them. The answer is about 5 milligrams. 5 milligrams. That is less than a grain of rice. It is roughly the weight of a single grain of sand, or 2 or 3 eyelashes. Sweep out an entire light year of space through a doorway-sized opening, and the total haul, all of it, everything that was in the way, would sit unnoticed in the palm of your hand. That is the first answer, and it is the one that makes the crossing sound trivially clean. Now here is the second. Do not take a column. Take a cube. 1 light-year on every side, a box the size of the unit itself, the same amount of nothing that we spent the first 3 parts of tonight failing to visualize. Same gas. Same 3/10 of an atom per cubic centimeter. Nothing has changed except the shape of what we are measuring. That cube contains about 70 times the mass of the Earth. 70 Earths. Not 70 Earths worth of stars or planets or debris. There are no stars in it. We will come to that 70 Earths worth of loose hydrogen, floating so thin that a laboratory would call it a perfect vacuum, adding up across a volume so large that the total becomes planetary. And that is the figure for our own unusually empty corner. Out in the ordinary interstellar medium of the galaxy, where the density is closer to 1 atom per cubic centimeter rather than 3/10, the same cube holds something in the region of 200 Earths. Even inside the local bubble, the hollowed-out cavity that is the emptiest thing anywhere near us, a cubic light-year still weighs about 12 Earths. There is no setting on this dial where the answer comes out small. The most rarefied space in our part of the galaxy, measured over the standard interstellar unit, still comes to more matter than every planet in the solar system put together, several times over. And both of those numbers describe the same gas at the same thinness. Nothing about the substance changed between the 2 paragraphs. What changed was how much of it we looked at, and the reason the answers feel incompatible is that our intuition for volume gives out long before our intuition for length does. We can just about hold a light year as a line. We cannot hold it as a box at all. Widen a light year into 3 dimensions, and it swallows planets. I find this the single most useful thing to know about interstellar space, and it is almost never said. The gap between the stars is not empty. It is thin. Those are different words, and they mean different things, and everything that happens for the rest of tonight follows from the difference. Empty means there is nothing there, and nothing can happen. Thin means there is something there, spread out, waiting, in quantities that do not matter at all if you are moving slowly, and matter enormously if you are not. Let me stop here for a moment, because we are about halfway through, and I want to put the pieces on the table together before we go any further. We started with a plate and a walk of 260 meters, and a number with 15 zeros in it. We found that the name of the unit was chosen in 1851 for a magazine, specifically to make that number sit comfortably in a reader's head. We measured the crossing with the fastest things we have ever built and got 17,000 years from Voyager and 1,500 from a probe that cannot hold its speed. We found out why that curve refuses to bend, because the price of speed rises as the square, forever, and there is no cleverness that argues with a receipt. And we found that physics does offer one genuine discount on the distance, and that it activates only on the far side of the wall. So the picture so far is a long, expensive, empty crossing. Long, we have covered. Expensive, we have covered. And now, in the last few minutes, empty has just quietly stopped being true. There are 70 Earths of hydrogen in the box, and a ship has to get through all of it. At walking pace, that is nothing at all, 5 milligrams down a doorway, brushed aside without noticing. But we have just spent an entire part of this video establishing that walking pace is not an option, that anything resembling a journey requires a substantial fraction of the speed of light, and that the faster you go, the more of that gas arrives per second, and the harder each piece of it hits. Which means the thing we have been calling the empty part of the problem is about to become the dangerous part of it. And the arithmetic on that is worse than the arithmetic on the fuel. Stand outside in light rain and nothing happens to you. drive through the same rain at 70 miles an hour with the window down and it stings. Nothing about the rain changed. The drops are the same size, falling at the same speed, spaced the same distance apart. What changed is how many of them arrive per second and how hard each one lands, and both of those are entirely about you. The weather did not become violent. You did. That is the whole of this part of the video, and it is the reason the last part matters. We have established that the space between the stars contains about 3/10 of an atom per cubic centimeter. At walking pace, that is beneath notice. Voyager 1 has been flying through it for 49 years, and it has not been meaningfully touched by any of it. At 17 kilometers a second, interstellar hydrogen is not a hazard. It is a rumor. But we have also established that 17 kilometers a second gives you a 17,000-year crossing, and that anything resembling a journey requires a substantial fraction of the speed of light. So let us take the most credible proposal anyone has actually put on paper, a light sail, pushed to about 20% of the speed of light, and ask what the gas does at that speed. A single hydrogen nucleus, hitting the front of that ship, arrives carrying about 19 million electron volts of energy. That number will not mean much on its own, so here is where it sits. Chemistry, every reaction in your body, every fire, every explosion of every conventional kind happens at energies of a few electron volts. A few. What is arriving at the front of that sail is 19 million of them per particle, which puts it squarely in the range of nuclear physics. These are not impacts in any sense a material scientist would recognize from ordinary engineering. They are the sort of collisions that particle accelerators are built to produce deliberately, at great expense, under laboratory conditions, one at a time. And the ship does not receive them one at a time. It receives them continuously, from the moment it reaches speed until the moment it stops, which in this case is never. A ship crossing a light year at 20% of light speed sweeps up something on the order of 100 million billion hydrogen nuclei for every square meter of its leading face over the course of the crossing. It is not traveling through a vacuum. It is traveling inside a particle beam of its own making, aimed permanently at its own nose, for the entire journey, and it cannot switch the beam off without stopping, which it also cannot do. The published analyses of what that does are sobering in a very particular way, because they are not dramatic. Nothing explodes. What happens is erosion, a slow, even relentless removal of material from the leading surfaces, atom by atom, along with damage to the structure of the material underneath as those nuclei bury themselves and stop. The estimates for an interstellar crossing at these speeds come out at something on the order of a fraction of a millimeter of surface loss, plus deeper damage tracks behind it. For a solid hull, that might be tolerable. For the thing actually being proposed, a sail a few atoms thick, weighing a gram, whose entire function depends on remaining perfectly reflective and perfectly intact, a fraction of a millimeter, is not damage. It is the whole object. And that is the gas, which is the gentle part. There is also dust. About 1% of the mass out there is solid, irregular grains, most of them smaller than a wavelength of light. Nobody knows precisely how many are along any given route, because we cannot see individual grains, only their collective shadow. But suppose the ship meets one that weighs a single milligram. Not a pebble, not a stone. A milligram, a grain of fine sand, the sort of thing you would not notice on your fingertip. At 20% of the speed of light, that grain arrives carrying roughly 1 billion joules of energy, which is comparable to about half a ton of high explosive. 1 grain of sand, half a ton of TNT. And the ship has no way of seeing it coming, No way of dodging it if it did, and no way of surviving it if it hits anywhere important. People have thought hard about how to survive this, and the proposals are ingenious in a way that tells you how bad the problem is. One idea is to turn the sail edge on for the crews to fly it like a needle rather than a sheet, so that the surface presented to the oncoming hydrogen is a few square centimeters instead of several square meters. Another, from an older and much larger design, was to send a cloud of dust ahead of the ship, a screen of particles fired forward to detonate anything solid before the vehicle arrived, so that the ship flies through the debris of its own advance warning rather than into the object itself. A third is simply to accept the losses, to build the leading face out of a material you expect to lose, and to make it thick enough that there is still something behind it when you arrive. Every one of those is a real engineering answer, and every one of them costs mass, or complexity, or both. And I should be honest about the state of the knowledge here, because it is worse than the numbers make it sound. Nothing has ever flown at these speeds. Not a probe, not a pellet, not a fragment. Every figure in this part of the video comes from calculation and from laboratory work done at speeds thousands of times lower, extrapolated upward into a regime nobody has ever observed. The estimates could be pessimistic. They could also be far too kind, because the density of dust along any particular route is not measured and not measurable with current instruments. We know the average, in the way you might know the average rainfall of a continent, and we have no idea whether the particular line between here and anywhere contains a thicker patch. You would find out by flying into it. For a crew, there is a further layer that the sail proposals get to ignore. A hydrogen nucleus at 19 million electron volts does not politely stop at the hull. It goes through, and it produces a shower of secondary particles on the way, and those go through as well. The forward-facing surfaces of a fast ship are not merely eroding, they are a continuously operating radiation source, pointed inward, running for the entire journey, powered by the emptiness the ship is crossing. The shielding required to sit behind that for years is measured in meters of dense material, and meters of dense material is exactly the mass the fuel arithmetic cannot carry. I want to point out the shape of this, because it is the shape of the entire subject, and it keeps recurring in different costumes. Every solution to the light year converts itself into a different problem of exactly the same size. Go slow, and the journey outlasts the civilization. Go fast, and the fuel bill becomes planetary. Pay the fuel bill, and the gas you are crossing turns into a particle beam. Shield yourself from the beam, and the shield has mass. And mass is the thing the fuel bill was calculated on, so every kilogram of protection buys itself another 100 kilotons of acceleration cost, and the receipt from 3 parts ago comes back with a larger number on it. Reduce the mass to nothing, so the fuel bill is payable, and now you have a sail thin enough to be destroyed by the very hydrogen you were trying to protect it from. There is no arrangement of these constraints that closes. Push on any one of them, and the others tighten. It is the single most telling thing about this problem, and it is why I do not think it is a technology problem at all. And notice what has happened to the 2 quantities we started with. At the beginning of tonight, distance and speed were separate things. A light year was how far, and velocity was how fast, and the second was the tool you used to defeat the first. They are not separate anymore. Going faster does not reduce the amount of universe in your way. It concentrates it. Every gain in speed is paid for in the same currency it was supposed to earn. This is what it looks like when a quantity that has been dressed up as a distance turns out, underneath, to be a rate wearing the clothes of a distance you cannot outrun it, because it was never a length. It was always a statement about how fast anything is permitted to get anywhere. So we now have a second real answer to the question in the title, and it is a better one than the first. It is not simply that a light year takes a long time. It is that going fast enough to shorten the wait converts empty space into the thing that stops you. The emptiness, which was the one part of the problem that looked free, turns out to be the part with a temper. 70 Earths of hydrogen, so thin that a laboratory would call it perfect vacuum, and every atom of it becomes ammunition the moment you try to hurry. Which leaves one last hope, and it is the one people usually retreat to when the ships stop working. Fine, we say. Forget the crew. Forget the arrival. Send something small and cheap and fragile, accept that it will never come back, and simply have it look and tell us what it saw. That is a reasonable retreat. It is the plan every serious proposal falls back on. And there is an arithmetic problem sitting in the middle of it that is, in some ways, the quietest and worst thing in this entire video, because it has nothing to do with getting there at all. There is a lamp somewhere in the room with you, or there was before you turned it off. Move twice as far away from it, and it does not become half as bright. It becomes a quarter as bright. This is one of those facts that everyone half knows and almost nobody carries around, and it is about to do more damage to the idea of interstellar travel than anything we have discussed so far. Light spreads out. So does radio, which is the same thing at a longer wavelength. A signal leaving a transmitter does not travel as a beam of fixed width. It opens out as it goes, and the same amount of energy has to cover a larger and larger surface. Double the distance, and you have 4 times the area to cover with the same power. 10 times the distance, 100 times the area. It is the same square that showed up in the fuel arithmetic, appearing again in a completely different discipline, which is one of those things that stops feeling like a coincidence after a while. Now, put Voyager 1 back in the picture, because it is the best real-world demonstration in existence. Voyager transmits on about 23 watts. That is less than the bulb in a fridge, less than a phone charger, a genuinely trivial amount of power. It is currently something like 170 times the distance from the Earth to the Sun. And by the time that 23 watts has spread across all the space between there and here, the amount arriving at the Earth is so small that describing it in ordinary units is almost meaningless. It is a tiny fraction of a billionth of a billionth of a watt, one of the faintest deliberate signals that human beings have ever detected. We hear it. That is the astonishing part. We hear it with dishes 70 meters across, buildings that move, tracking a spacecraft nobody can see, listening for a whisper that has been traveling for the better part of a day. But it is important to understand why we can hear it, because the reasons are all things we will not have at a light year. We hear Voyager because we know exactly where it is, to within a hair, having tracked it continuously for 49 years. We know exactly what frequency it transmits on, because we chose the frequency and built the transmitter. We know exactly when it will transmit, because we told it to. We know exactly what the signal will look like, because we wrote the format. And knowing all of those things lets a receiver pull a signal out from underneath, a noise that is far louder than the signal itself. You can find almost anything if you know precisely what you are looking for and precisely where. Now take that same 23-watt transmitter and put it 1 light year away. A light year is 63,241 times the distance from the Earth to the Sun. Voyager is at 170. So the transmitter has gone about 370 times further out, and because of the square, the signal arriving is not 370 times weaker. It is roughly 138,000 times weaker. Take a signal that is already at the outer limit of what the largest antennas on Earth can detect, and divide it by 138,000. That is what a probe at 1 light-year sounds like. Which is to say, it does not sound like anything. You would need an enormously more powerful transmitter, which needs an enormously larger power supply, which has mass, which goes back onto the receipt. Or you would need a much larger dish here, which is possible but not by 5 orders of magnitude. Or you would need to send the signal as a narrow beam rather than letting it spread, which is the actual answer, and which requires the probe to know precisely where Earth is, and to point at it with an accuracy that a gram of electronics traveling at 1/5 of the speed of light after 20 years alone in the dark is not obviously going to manage. Engineers working on these proposals have a phrase for this problem. One of them called communications the elephant in the room, and the description is fair. Almost all the public attention goes to the question of how to get something there. The question of how anything gets back is harder, less glamorous, and no closer to being solved. There is also the question of how much you could say, which is separate from whether you could be heard at all. The fainter a signal, the more slowly you have to send. You cannot cram information into a whisper. Voyager, at 1 light day, returns data at a rate of a few dozen to a few hundred bits per second, which is slower than the very first home modems, and about 1/1,000,000th of the speed of an ordinary domestic connection today. It takes hours to send back a single simple measurement. Push the same craft out to 1 light-year, and the achievable rate collapses along with the power, until you are no longer talking about images or data or science at all. You are talking about whether a single bit, one yes, one no, one confirmation that something is still alive out there, can be got across in a human lifetime. That is what one engineer meant when he said that the entire value of such a mission might come down to 1 bit. Not 1 photograph. 1 bit. And he was not being defeatist. He was being precise. And he was arguing that even 1 bit would be worth the whole undertaking, which is a thing I find genuinely moving, and also a very clear description of how little the physics permits. The usual retreat from this is to stop trying to converse and simply broadcast. Build a beacon, point it roughly homeward, transmit the same short message over and over for years, and let the receiver on this end integrate the signal over enormous stretches of time until it rises above the noise. That works, in principle, and it is how you would actually do it. It also means the probe cannot be asked anything, cannot be told anything, and cannot report anything. It was not designed in advance to report. It is not a correspondent. It is a smoke signal, sent once from a fire you cannot see. And then, underneath the power problem, there is the time problem, which is not an engineering issue at all. It is simply what the distance is. 1 light year means a signal takes 1 year to arrive. An answer takes another year. 2 years, minimum, for a single exchange of question and response. Sit with what that does to the idea of operating something. Every space mission ever flown has been a conversation. Something goes wrong, an instrument misbehaves, a sensor reads strangely, a mechanism sticks, and the ground team looks at the data, thinks about it, sends a command, waits, looks at the result, and tries something else. Voyager has been kept alive for nearly half a century by exactly that process, repeated hundreds of times, and by engineers who have occasionally saved it from failures that would otherwise have ended the mission. At 1 light day, that loop takes 2 days. Slow, frustrating, and workable. At 1 light year, the loop takes 2 years. Ask a question, and the person who asked it has had 2 birthdays before the answer arrives. A 10-step troubleshooting sequence which is a modest, ordinary, unremarkable piece of engineering work, the kind of thing a team might get through in an afternoon, takes 20 years. A career. So there is no operating the thing. There is no fixing it, no adjusting it, no changing its mind. Whatever you send has to be completely autonomous and completely correct at the moment of launch, because it will get no help of any kind, ever. And by the time you learn that it failed, it will have been failing for a year. And here, I think, is the part that actually stays with me, because it is not about machines. For all of tonight, we have treated arriving as the goal. Every calculation has been aimed at the moment of getting there. But arriving is not the same thing as being in contact, and 1 light year is the distance at which those two come apart completely. You can be there and be unreachable. You can succeed entirely, cross the gap, survive the gas, arrive intact, function perfectly, and still be, from the point of view of everyone who sent you, indistinguishable from a failure, because nothing you say arrives loud enough or soon enough to matter. That is a strange kind of distance. It is not the distance at which you cannot go. It is the distance at which going stops meaning anything, because the thread back does not hold. 1 light year is where a species stops being able to have a conversation with itself. And I have to add one more thing, because we are still not being pessimistic enough. Every number in the last 20 minutes has quietly assumed something that is not true. It has assumed that the destination is sitting still, that there is a fixed point out there, 1 light year away, waiting patiently for 17,000 years while we come and get it. Nothing in the sky has ever done that. Not one star, not for 1 night. In 1718, in London, a man is sitting with 2 lists of numbers in front of him. One of them is about 1,500 years old. The man is Edmund Halley, who is remembered for a comet and who did a great many other things besides. The old list is a star catalogue inherited from Greek antiquity positions of the brightest stars, recorded by astronomers who died before the Roman Empire existed. The new list is the best contemporary measurement. Halley is comparing them, position by position, and finding, as expected, that they agree. Except for 3. Sirius has moved. Arcturus has moved. Aldebaran has moved. Not by much by amounts you would never notice in a human lifetime, by fractions of a degree, but by amounts far too large to be explained away as errors in the old catalogue. 3 of the brightest stars in the sky are not where the Greeks left them. It is difficult now to feel how strange that was. For the whole of recorded history up to that afternoon, the phrase, "for what is overhead at night," was "the fixed stars," and the word "fixed" was not poetic. It was the technical description. The planets wandered, that is what the word planet means, and the stars did not. That was the fundamental division of the sky, taught to every navigator and every astrologer and every astronomer for 2,000 years. Halley found that it was wrong. The stars are not fixed. They are merely slow. We call it proper motion, and every single star in the sky has it, and it is going to take apart the last assumption this video has been standing on. Because every number I have given you tonight, 17,000 years, 1,500 years, the receipts, the fuel, the erosion, has quietly assumed there is a destination sitting still out there, 1 light year away, waiting for us with the patience of a bus stop. Nothing in the sky does that. Not one object, not for 1 night. The champion, as it happens, is nearby and easy to name. In 1916, an American astronomer named Edward Emerson Barnard measured the proper motion of a faint red star in the constellation Ophiuchus and found it to be the largest ever recorded, 10.3 seconds of arc, per year. It still holds the record. The star is now simply called Barnard's star, and it sits about 6 light-years away, which makes it one of the closest things to us in the universe. 10.3 arcseconds a year does not sound like anything. It is about a 350th of a degree far below what an eye can see, far below what most telescopes could have caught before photography. But let it run. Over a human lifetime, Barnard's star moves 1/4 of a degree across the sky. That is about half the width of the full moon. A person who photographed it as a child and again as a pensioner would find it visibly displaced against its neighbours by an amount they could measure with a ruler on the 2 prints. Barnard's star has, incidentally, been the site of one of the longest-running quiet embarrassments in astronomy, and it is worth a sentence because it says something about how hard this measuring is. In the 1960s, an astronomer named Peter van de Kamp announced that the star's motion showed a wobble evidence, he said, of planets. He had been photographing it for decades. The claim stood for years and was widely believed. It eventually turned out that the wobble appeared at the moment the telescope's lens had been serviced, and that other observatories, looking at the same star, saw nothing. The planets were an artifact of the instrument. Only in the last few years, with spectrographs sensitive enough to detect the star being tugged at speeds slower than a walking pace, have genuine planets been found there, several of them, all smaller than the Earth. The right answer took 60 years and better machines, and the wrong answer was produced by a careful man doing careful work with the best equipment of his day. And that is only the sideways part. Barnard's star is also coming towards us, at about 110 kilometers per second. Put the sideways motion and the towards motion together, and its actual speed through space, relative to the Sun, is 142.6 kilometers per second. Now do the thing that turns this from an astronomical curiosity into the heart of tonight's problem. Voyager 1, at 17 kilometers a second, needs about 17,600 years to cross 1 light-year. In those same 17,600 years, Barnard's star, traveling at 142 kilometers a second, carrying nobody, burning nothing, having made no plans and solved no engineering problems, covers about 8.5 light-years. The star is faster than the ship. Not marginally. By a factor of more than 8. I want to let that sit, because it inverts the picture almost everybody carries. Every image we have of interstellar travel puts us in motion against a still background. The ship glides forward. The stars hang there. That is how it looks in every film, every illustration, every animation, and it is the exact reverse of the truth. We are not the moving thing. We are the slowest object in the frame. The stars are crossing these distances constantly, in every direction, at speeds we cannot match. And they have been doing it for billions of years, and they will still be doing it long after every machine we have ever launched has stopped. The galaxy is not a room we are trying to cross. It is a room in which everything else is already moving faster than us, and has been the whole time. And now I have to complicate my own point, because there is one exception, and it turns out to make things worse rather than better. We are moving too. The Sun is not sitting still in the galaxy. It is orbiting the center at something like 230 kilometers a second, carrying the Earth and every planet and every one of us along with it. That is faster than Barnard's star. It is more than 1,000 times faster than Voyager. Right now, tonight, without any engine and without any decision, you are covering 1 light year roughly every 1,300 years. Read that again, because it is the most quietly absurd fact in this entire video. The distance we have spent the last hour establishing is impossible, the one that takes our fastest machine 17,000 years. You are personally crossing every 13 centuries, lying in bed, for free. And it gets you nowhere. It has never got anyone anywhere. Because everything nearby is moving with us, in roughly the same direction, at roughly the same speed, held in the same great orbit by the same galaxy. The whole neighborhood is traveling together. We are all in the same carriage on the same train, and the distances between the seats do not change because the train is moving. Which tells you something precise about what the scarce resource actually is. It is not motion. We have motion in abundance. We are drenched in it. We have never for one instant been still. What we do not have, and cannot get, is motion relative to our neighbors. The universe hands out speed freely and charges an impossible price for the only kind that closes a gap. Let me put you inside what that means. You are aboard a ship, and it has been flying for 17,000 years. You are not the crew that launched. Nobody aboard has ever met anybody who saw the Earth. Everything is working. The reactor is fine. The hull is holding. The navigation logs show the ship has covered 1 light year exactly as intended, to within a fraction of a percent, on a course laid in before any of this existed. By every internal measure, the mission is a triumph. And you go to the forward port, and the sky is wrong. Not damaged. Not obscured. Wrong. The star you were aimed at, the one that was ahead and slightly to the left at departure, the one every chart aboard is built around, is over your shoulder. It has swung roughly 50 degrees across the sky in the time you have been flying. 50 degrees is the difference between something directly overhead and something halfway down towards the horizon. If you had launched pointing at it and simply held that heading, you would now be looking at it out of a side window while continuing to fly, faithfully and correctly, at absolutely nothing. Nothing has failed. No instrument is broken. No calculation was wrong. The aim was simply taken at a room that was moving, by people who had every reason to believe they had accounted for it, and who could not have known that the accounting itself had to be redone continuously for 17,000 years by somebody watching. That is the second half of this problem, and it is the half that no amount of engineering touches. It is not about how fast you can go. It is about the fact that there is a moving quantity, and the interval you need in order to arrive is long enough for there to become somewhere else. Now, in fairness, this cuts both ways, and one of the directions it cuts is genuinely lovely. Alpha Centauri, the nearest star system to us, is not sitting still either. It is coming towards us, at somewhere around 20 to 22 kilometers per second. It has been getting closer for a very long time, and it will keep getting closer for tens of thousands of years yet. Sources differ a little on the exact figures you will see closest approach, quoted anywhere from about 27,000 to about 30,000 years from now, at a distance of somewhere between roughly 2.9 and 3.26 light years. And the honest thing to do is give you the range rather than pretend to a precision that is not there. But the direction of travel is not in doubt. The nearest star is closing on us. And here is the arithmetic that goes with that, which I have never been able to decide how to feel about. In the 17,600 years, it would take Voyager 1 to cross 1 light year. Alpha Centauri closes something like 1.25 light years of the gap on its own. Doing nothing beats flying. If humanity had launched a Voyager-class probe at Alpha Centauri and simultaneously done absolutely nothing at all, the doing nothing would have covered more ground. The stars are not merely faster than us. On our best day, with our best machine, they are better at reducing the distance between us than we are. That is not, incidentally, a reason to give up, and I do not want it to land as one. It is a reason to notice something about the shape of the situation, that the distances are not fixed features of the universe waiting to be beaten, but a slowly changing arrangement that will keep changing whether or not anybody does anything about it. In roughly 1.3 million years, a small star called Gliese 710 is expected to pass within about a light year of the Sun, closer than anything is now, close enough that it will move through the outer parts of our own system. The nearest star is not a permanent title. It is a rotating position, held for a few tens of thousands of years at a time. We can say all this with confidence because of a spacecraft that has quietly done more for this subject than any rocket ever will. The Gaia mission has measured positions, distances, and motions for close to 2 billion stars at a precision that amounts to picking out the width of a human hair from 1,000 kilometers away. What that gives us, for the first time in history, is not a photograph of the sky but a film of it. We can run it forward. We know, to a reasonable approximation, what the night sky will look like in 10,000 years, and in 100,000. It will not look like this. Within roughly 50 to 100,000 years, the constellations dissolve. The plough loses its shape. Orion comes apart. The patterns that every human culture in history has named and told stories about and navigated by are a temporary arrangement, currently about halfway through their run, and they are already visibly deforming on the timescale of a single interstellar crossing. 17,000 years is not, in the life of a galaxy, a long time. It is not long enough for a star to age noticeably or a constellation to be unrecognizable. It is exactly long enough for the target to have moved further than the ship. So we have added a fifth failure to the pile, and it is qualitatively different from the other four. Propulsion, energy, materials, and communications are all things that better technology could, in principle, improve, even if the improvements are hopeless in practice. This one is not. You could build a perfect ship with unlimited fuel and no erosion and a flawless radio, and it would still have to aim at a target that will not be there, using a prediction that has to hold for longer than our species has had agriculture. Which raises the obvious question. And it is a question I did not think to ask until quite late in putting this together. We have been talking all night about crossing 1 light year. We have been picturing it as a journey towards something. But hold on. What is actually 1 light year away? Not 4. Not 6. 1. What sits at the far end of the unit itself? What is the thing you would arrive at? The answer is one of the strangest facts in astronomy, and it is the reason this whole thing feels endless. Think about a long drive at night, on a motorway, in the dark. What actually gets you through it is not the road. It is the furniture beside it. The sign that says 40 miles to the next town. The service station at the halfway point. The junction numbers counting down. The bridge you remember from last time. Take all of that away, same road, same distance, same car, but no signs, no exits, no lights, nothing but tarmac unrolling in the headlights for hour after hour, and the drive becomes a different experience entirely, even though nothing about the journey has changed except the absence of things to measure yourself against. We now have to look at what is actually beside the road, over 1 light year of interstellar space. Nothing. And I mean that with a precision I did not expect to be able to give it. Astronomers have measured how thickly stars are packed in our part of the galaxy, and the answer comes out at around 4,000ths of a star per cubic light year. Turn that over, and it means 1 star for every 250 cubic light years of space. Now take the unit itself and draw it as a sphere. A ball 1 light year in radius, centered anywhere you like out there. in ordinary space near us. That ball has a volume of a little over 4 cubic light-years. Multiply that by the density, and you get the expected number of stars inside it. About 1/60th of a star. Which is to say, pick a point at random in our neighborhood, draw a sphere 1 light-year across in every direction from it, and there is roughly a 98% chance that the sphere is completely empty of stars. Not sparsely populated. Empty. No suns, no planets, no worlds, no light sources of any kind. Just hydrogen at 3/10 of an atom per cubic centimeter, and dust and the light of other things passing through on its way somewhere else. And that arithmetic explains something I flagged at the very beginning of tonight and have been carrying since. Every other unit of distance we use is anchored to a thing. A meter is roughly a stride it came from a human body, and it still fits one. A kilometer is a walk you could take before lunch. A mile is an old marching distance. An astronomical unit is the Earth's own orbit, a real circle around a real star. A thing you can draw. Even a parsec, ugly as it is, comes directly out of a measurement anybody can, in principle, make. The light year is anchored to nothing at all. There is no pair of objects near us separated by 1 light year. There is nothing you can point at. The nearest star to the Sun, Proxima Centauri, is 4.2465 light-years away, more than 4 times the unit. The next system out is a little further. Barnard's star is nearly 6. There is no object anywhere in our neighborhood sitting at the far end of a single light-year, and there is no object sitting at the halfway point, and there is no object at any point. The light-year is smaller than the spacing of every single thing it is used to describe. That is the arithmetic underneath the feeling. It is not a distance between 2 places. It is a subdivision of the gap between places, a ruler shorter than the shortest thing it measures, used because a smaller number is easier to say. 9.5 trillion kilometers, and not one landmark in it. That is not rhetoric. That is the measured stellar density of the solar neighborhood, worked out and stated plainly. It is worth saying that this is a fact about where we happen to live, not a law of the universe, and there are places where it is not true. Out in the halo of the galaxy, there are ancient, tightly packed balls of stars called globular clusters, a few 100,000 suns each, gravitationally bound, some of them older than the disk of the Milky Way itself. In the cores of those clusters, the stars are packed thousands of times more densely than they are here. Typical separations drop to a fraction of a light-year. If you stood on a world in there, the night sky would have hundreds of stars in it brighter than Venus, some of them bright enough to read by, and a light-year would not be a subdivision of a gap. It would be a real distance between real neighbors with things in it, and a journey of 1 light-year would be a journey to somewhere. Nobody lives there, as far as we know, and the physics of those cores makes stable planetary orbits difficult. But it is worth knowing that the emptiness we are describing is a local condition. We are in the thin part. The unit was invented by people living in the thin part, and it fits the thin part badly. And I want to say something about what the view would actually be like, because I think it is the piece most people have never been given. Aboard a ship on that crossing, nothing happens to the sky. Not slowly. Not at all. The stars do not stream past the windows. There is no sensation of speed, because there is nothing close enough to move against. Over the entire 17,000 years, the star you are heading towards does not visibly grow. The one behind you does not visibly shrink. The constellations do drift over tens of thousands of years. But on any given night, any given century, the view out of the forward port is identical to the view the night before. Generation after generation would look out at precisely the same picture, know intellectually that they had covered trillions of kilometers since the last one, and see no evidence of it whatsoever. It would be the most beautiful and the most static thing anyone has ever looked at. And it would never change. And this, I have come to think, is the real answer to why this particular distance feels the way it does, why it produces that specific sensation of a thing that does not conclude. Every other hard journey in human history had a structure. It had a middle. The crossings of the Pacific were terrifying and lethal, and they had islands, places to stop, to take on water, to know that progress had been made. The Atlantic had no islands, but it had a far shore reachable within a season, and a bearing, and the certainty that if you kept west, the water would end. Polar expeditions had depots and caches, unknown coastlines. Even the journey to the moon had the moon in the window, getting visibly bigger. A light year has no middle. It has no depot. It has no landmark to check yourself against, and it has nothing at the end of it either, because it is too small a unit to reach anything. There is no moment on the crossing where anybody could say we are halfway, because halfway would look precisely and exactly like the start, and precisely and exactly like the end, and precisely and exactly like every other second of the 17,000 years. That is what people mean, I think, when they say it never ends. Not that the distance is infinite, it is not, it has a number. We said the number in full at the beginning. But that a road with nothing on it does not feel like a road at all. It feels like a condition. Endlessness is not a property of the length. It is what happens to a length when you remove everything that could mark progress through it. And human beings do not run on distances. We run on milestones. Every enterprise our species has ever sustained across generations, a cathedral, a canal, a dynasty, a science, has been sustained by intermediate results. Something finished, something visible, something to hand to the next set of hands and say, look, this much is done. Take away the ability to know how far along you are, and the enterprise does not become harder. It becomes a different kind of thing, one we have never successfully done. Let me put the numbers side by side one final time, because they are worth having in one place before we go on. 1 light year is 63,241 times the distance from the Earth to the Sun. It takes light 1 year to cross. Our fastest object is about 17,600, and a person walking around 216 million. It contains 70 Earths of hydrogen, so thin that a laboratory would call it a perfect vacuum, and every atom of that becomes ammunition at speed. It attenuates a signal from the edge of detectability down to nothing. It moves while you cross it, and there is a 98% chance that any given sphere of that size anywhere near here contains no star at all. That is the smallest unit on the map. Although, and I am going to leave this here and pick it up at the end, because it is the answer to the question in the title, and I do not want to spend it yet. I said a moment ago that there is nothing 1 light year from here. That is very nearly true, and it is what every chart and every diagram will tell you, and it is the assumption that has been sitting underneath every calculation tonight. There is one exception. It is not a star. It is not another system. It has been on every map of the solar system you have ever seen, usually as a faint sphere in the corner of the diagram with a label nobody reads. And once you know what it is, the entire shape of this problem turns over. Hold that. We will come back to it. Now, when a case has been laid out like that carefully, with the numbers, Without exaggeration, something predictable happens. People start looking for the exit. I do it too. It is a completely reasonable response to a closed argument, and it is not weakness or wishful thinking. It is how minds work when they are given a wall. And there are exits on offer. 4 of them, roughly, and they get proposed constantly. One of them is nonsense. One of them is a misunderstanding of how energy works. One of them is genuinely serious physics that deserves to be treated with respect. And one of them cannot be argued with at all, for reasons that are themselves interesting. I want to walk you through all 4 calmly and check each door. There is a photograph that gets posted over and over whenever a video like this one goes up. It is a picture of a star field, and somebody has drawn an arrow on it, and the caption says something like, "They measured this how exactly?" It is a fair question, and it deserves a proper answer rather than a sneer, so let us take it first. The first door is the claim that the distances are simply wrong, that a light year is an extrapolation stacked on an assumption, stacked on a model, and that the stars are far closer than we are told. The answer is that the nearest stars are not measured by any model at all. They are measured by an angle. Everything else in astronomy, the brightness of a certain kind of exploding star, the pulse rate of a certain kind of variable, the redshift of a distant galaxy, all of that is calibrated against something, and you can reasonably ask what it is calibrated against. Parallax is not. It is trigonometry of the kind taught to 15-year-olds. You look at a star in January and again in July from 2 positions 300 million kilometers apart, and you measure how far it appears to shift. That is the whole method. Bessel did it in 1838 with lenses and patience. The Gaia spacecraft has now done it for close to 2 billion stars, at a precision fine enough to pick out a hair's width from 1,000 kilometers away. And there is a clean, checkable consequence. If the stars were much closer than stated, the angles would be much larger, and they would have been obvious centuries ago. Obvious to Copernicus, obvious to Galileo, obvious to anyone with a decent instrument. The absence of visible parallax was the single strongest argument against the Earth moving at all, for 200 years. It was not a small effect that got overlooked. It was a missing effect that nearly sank the whole theory, and it was missing because the distances are enormous. There is a second check anybody can make. If the stars were nearby, they would show disks in a telescope, the way planets do. Point any instrument ever built at any star other than the Sun, and it remains a point. Every one. That is not an inference. That is a direct observation of distance, available to any amateur with a garden. And there is a third check, which is the one that would be hardest to arrange if anybody were arranging anything. Parallax is not the only way to get a stellar distance. You can get one from the way certain variable stars pulse, from the way pairs of stars eclipse each other, from the ringing of sound waves inside a star's own body, from the way clusters of stars sort themselves by color and brightness. These are entirely separate branches of physics, developed by different people at different times for different reasons, using different instruments and different assumptions. They agree. For a conspiracy to be sitting underneath the distance to the stars, 6 unrelated fields would have had to be coordinated, quietly, for 2 centuries, by people who mostly disliked each other. The second door is the claim that somebody has already solved this and is not saying, "I understand the appeal." And I am not going to argue about institutions or secrecy because the argument does not need to go there. It only needs to go to the electricity bill. The energies we have been talking about tonight are not laboratory energies. They are planetary energies, the output of entire civilizations, converted with perfect efficiency into forward motion. Energy on that scale is not a thing that can be quietly done. It shows up as waste heat, because everything does. It shows up as infrastructure, the plants, the grid, the mining, the industry required to build and feed the machine. It shows up in the sky, as an object accelerating. There is no version of a hidden interstellar program that does not leave a mark the size of a national economy, and no such mark exists. The problem with the secret solution story is not that people are trustworthy. It is that thermodynamics is loud. The third door is the serious one, and I want to be careful with it, because it is real physics, and it is often dismissed too quickly. There are solutions to Einstein's equations of general relativity that permit effective travel faster than light-warp geometries, in which a region of space is contracted ahead of a ship and expanded behind it, and traversable wormholes, in which two distant regions are connected directly. These are not inventions. They are things somebody sat down and derived, honestly, from the actual mathematics of gravity, and the papers are in the literature and the work continues. What every one of them requires is an ingredient. Negative energy density, matter with properties that have never been observed in any laboratory, anywhere, ever. In the earliest published versions, the quantity needed was comparable to the mass of a large planet. Subsequent work has reduced the requirement enormously, and some recent papers explore geometries claimed to need no exotic matter at all at the cost of speeds well below light, which puts them back inside every constraint we have discussed tonight. So the honest position is this: the equations of general relativity do not forbid it. The equations describe a door. Nobody has ever found the material the door is made of, and there is no established physics that says the material exists. A solution that requires a substance nobody has ever seen is a description of a door, not a key. That is not a dismissal, it is a location. It says where the work is, and the work is real. The fourth door is the one that cannot be argued with, and its unarguability is the whole point. Some people look at everything in this video and conclude that it is deliberate, that the distances are a quarantine, or a render limit, or a designed separation, that the reason the numbers come out this way is that they were set to come out this way, by something, for a reason. There is no argument against that, and I am not going to pretend there is one. It cannot be tested. Nothing could ever count as evidence for or against it, which is exactly what makes it a different kind of claim from the other three, rather than a competing answer to the same question. What can be said is that nothing needs to be invoked. The distances fall out directly of two measured quantities: the speed of light and how thinly stars are scattered through a galaxy. Neither is mysterious. Neither requires an intention behind it. You get a light year and its awkwardness and everything else tonight from those two numbers and nothing else. When the ordinary explanation is complete, adding a purpose behind it is a choice about how you like to feel, not a discovery about how things are. And people are entitled to that choice. It just is not the same activity as measuring. 4 doors. One of them is a misunderstanding of an angle. One is a misunderstanding of a power bill. One is a real corridor, honestly mapped, with a locked room at the end of it. And one is not a door at all. So, the case stands. And having stood it up as carefully as I know how, I want to spend a few minutes on the other side of it, because there is something that crosses light years constantly, effortlessly, in enormous numbers, and it arrived in this room while I was talking. If there is a window near you, and the sky outside is clear, something is coming through it right now that has already done the thing we have spent all night calling impossible. Starlight. Ordinary, unremarkable starlight, the kind nobody looks up at anymore. Every point of light in the sky tonight is sending a continuous stream of photons in every direction, and a very small number of them are arriving on the glass of your window and on the surface of your closed eyelids, and every single one of them has crossed a distance that no ship will ever cross. Not 1 light year. 4 for the nearest. 600 for the ones in the shape of Orion. 2.5 million for the faint smudge of Andromeda, which you can see with your own eyes on a good night from a dark place, a photon that left before there was anything on this planet that would have recognized it. They did it, carrying nothing. No fuel, no engine, no shielding, no plan. They did not slow down, they did not deviate, they did not degrade. Each one arrived carrying exactly what it left with, having crossed a gap that would ruin any machine we could build, and it did it without any effort at all. It is worth understanding why light gets away with this, because the reason is not a loophole. It is the same rule we have been running into all night, seen from the other side. Everything in Part 4, the receipt, the square, the 100 kilotons per kilogram, is arithmetic about accelerating mass. That is what the bill is for. Light has no mass. There is nothing to accelerate. A photon does not have to be got up to speed, because it has never done anything else. It is created already traveling at the speed of light, and it stops only when something absorbs it. The universe does not charge light for its journey, because there is nothing to charge for. It is not that light is exempt from the rule. It is that light is what the rule looks like when you take the mass out. So the universe does not have a closed border. It has 2 channels, and only one of them is open. Matter cannot make the crossing. Not in any practical sense, not on any timescale we can use, for all the reasons we have gone through. But information crosses constantly, in enormous quantity, in every direction, and it has been doing so since the first stars lit. Right now, tonight, this planet is being rained on by news from everywhere. Nobody has to build anything. It is simply arriving, all the time, whether or not anyone is awake to notice. And everything we know about anywhere else came in through that one channel. Every fact in this video, the density of interstellar hydrogen, the motion of Barnard's star, the distance to 61 Cygni, the composition of everything, the age of the universe was read off light that made a crossing we cannot make. We have never brought back a sample. We have never sent anyone. We have never touched a single thing that was not already inside the orbit of Neptune. Every scrap of knowledge we have about the universe beyond our own front step was delivered by photons that did the impossible for free and asked nothing. And because every one of those photons left at a different time, the sky is not a picture of a moment. It is a picture of many moments, layered on top of each other, arriving together and pretending to be simultaneous. The light from the nearest star left 4 years ago. The light from the middle star of Orion's belt left around 1300 years ago, when most of the languages spoken on this planet did not yet exist in their current form. The light from the faint smudge in Andromeda left before there were people. All of it lands on the same retina, in the same instant, and looks like one view. Nobody ever sees the sky. Everybody sees a stack of pasts, sorted by distance, delivered in order of how far each one had to come. I should add, for completeness, that matter does cross these gaps too. In 2017, an object was spotted moving through the solar system on a path that could only have come from outside it, and another followed 2 years later, and more have been found since. They are real. They made the crossing. They also took, in all likelihood, millions of years to do it. They were not aimed at anything. They carried nobody, and they are not stopping. So it is not that matter is forbidden. It is that matter crosses on the terms of the receipt enormously slowly, with no destination and no passenger, and that is precisely the arrangement we are trying not to accept. There is a trade underneath that, and it is worth naming. The channel that works cannot carry us. Light cannot stop, cannot look around, cannot decide, cannot choose what to bring, cannot come back and tell us what it was like. It arrives at the speed it always had, is absorbed, and ceases to exist. It is a messenger that cannot be sent, only received. Everything we have ever learned came from paying close attention to something that was not addressed to us. And the other channel, the one that could carry a person, that could bring back a sample, that could allow somebody to stand somewhere else and look up at a different sky, is the one with the receipt on it. That is the arrangement. It is not obviously fair, and it is not obviously unfair. It is simply how a universe with a speed limit and a rule about mass turns out to work. I find, and I say this without any melancholy in it, that this is the part of the subject I like best. Because the unit we have spent tonight tearing apart the light year, the awkward, disguised, unmanageable thing is named after the one process that beats it. There is something almost tender about that. We took the most humbling distance in the sky and named it after the thing that crosses it effortlessly, as though we could borrow a little of the achievement by using the word, which brings us, at last, all the way back round to the question in the title, and to the thing I promised you at the end of Part 10 and have been holding since. We have established that 1 light year is far worse than anyone thinks, and we have established 6 separate reasons why. But I have not yet told you the actual answer, because the actual answer is not any of those 6. It is something else, and it comes from asking a question so simple that it took me an embarrassingly long time to ask it. Where would you be if you did it? Suppose you managed it. Suppose everything went perfectly, the fuel, the shielding, the 17,000 years, all of it. You cross 1 light year. You stop, you look around, and you check the charts. Where, exactly, are you standing? Somewhere out in the dark, at about 60,000 times the distance from the Earth to the Sun, there is a lump of ice a few kilometers across, and it is turning around. It has been traveling outward for tens of thousands of years. It is moving so slowly now, a few hundred meters a second, slower than a rifle bullet, absurdly gentle that you could watch it and see nothing happen. But it is at the far end of its swing, and the outward part of its journey is finishing. And over the next few centuries it will stop receding and begin imperceptibly to fall. It is falling back towards the sun. It has never stopped being held. Out there, 60,000 Earth orbits from home, in the dark, in a place no instrument has ever seen and no probe will ever reach, that piece of ice is still on a leash, and the other end of the leash is a star it will not arrive at for another 20,000 years. That object is the answer to the question I asked at the end of the last part. Because when you cross 1 light year, when you spend the 17,000 years, pay the receipt, survive the hydrogen, hold the aim against a moving sky, and finally stop and look at the charts you are standing next to it. 1 light year is 63,241 astronomical units. And the Oort cloud, the shell of frozen bodies that surrounds the sun, that is the source of every long-period comet that has ever crossed our sky, that Jan Oort inferred in 1950 from nothing but the shape of their orbits, extends outward, on the commonly cited figures, to about 100,000 astronomical units. Some estimates take it further to 150,000. NASA gives the range as 10,000 to 100,000 and says plainly that the outer boundary is not a sharp line, because there is no sharp line to give. 63,241 is inside that. You have not left the solar system. You are still in it. You are in the outermost room of the same house you were born in, surrounded by objects that orbit your own sun, in a region the sun's gravity still owns, and the star you departed from is still the star that everything around you is falling towards. 17,000 years. 3 times the span of recorded history. The entire first unit of interstellar distance. And you have reached the far end of your own garden. There is something worth saying about how we know this, because it is one of the more remarkable pieces of reasoning in the whole of astronomy. Nobody has ever seen an object in the Oort cloud. Not one. It has never been photographed, never been detected, never been resolved by any instrument. The bodies out there are small, dark, unimaginably cold, and so far away that no telescope on Earth or in orbit has any prospect of picking one out. What Jan Oort did in 1950 was to look at the comets that come in. He took the long-period ones, the ones that arrive once and are not seen again for thousands of years, and traced their orbits backwards, and found 2 things. Their furthest points clustered at tens of thousands of astronomical units. And they came in from every direction on the sky, not from the flat plane the planets occupy, which told him that the reservoir was not a disk. It was a shell, surrounding everything, in every direction, at a distance nothing had ever visited. The largest structure in the solar system, holding perhaps a few Earths' worth of ice spread thin across a sphere light-years wide, and the entire case for it rests on where a handful of comets came from and where they were going back to. That is what is around you when you stop after a light year. Something we are confident is there, that nobody has ever seen, that still counts as home. So why is traveling 1 light year far worse than you think? Here is the answer, and it comes in 3 layers. The first layer is the one we spent most of tonight assembling. It is not that the crossing is hard in one way. It is that it is hard in 6 ways at once, and the 6 are unrelated. Propulsion, energy, materials, science, communications, biology, celestial mechanics, 6 separate disciplines with 6 separate limits, which have no business agreeing about anything, and which all deliver the same verdict at the same range. That is what makes it different from every other barrier in our history. A barrier with one cause has a weak link, and human beings are extraordinarily good at finding weak links. This one has no weak link, because it has no single cause. Solve any one of the 6 and the other 5 are exactly where you left them. The second layer is the one the name has been hiding since 1851. A light year is not a distance. It is a rate wearing the clothes of a distance. It is defined by how far the fastest possible thing gets in one trip around the sun, which means the number is not a statement about space at all. It is a statement about the maximum performance of the universe, written down as a length so that it will fit in a sentence. Nothing crosses a light year faster than 1 per year. That is not an engineering ceiling that a better century might raise. It is what the word means, and it follows that interstellar distance is not really distance. It is delay. When we say a star is 4 light years away, we are not describing how far it is. We are describing the minimum possible gap between anything happening there and anybody here being permitted to know. And then the third layer, which is the one I did not expect and which reorganized the whole subject for me. 1 light year does not go anywhere. It is not a journey between 2 places. It is a journey through the outskirts of one place, and the place is this one. The unit that we use to measure the distance between stars is smaller than the distance from the Sun to the edge of its own possessions. The first light year of any journey anyone ever makes from here is a light year spent inside the solar system. 9.5 trillion kilometers, and not one landmark in it, and it turns out there was a landmark. It was behind you. It was the thing you were inside of the whole time. That, I think, is what people are reaching for when they say a thing like this never ends. It is not that the distance is infinite. It is that at the end of the whole enormous crossing, you check the map, and you are still on the first page of it. The unit does not deliver you anywhere. You go the full length of the smallest measure on the chart, and you arrive somewhere that is still labeled with the name of the star you left. It never ends, because you never left. And now, gently, I want to turn it over, because there is another way to read exactly the same fact, and I do not think it is the sad one. The Sun's grip reaches out somewhere between 1 and 2 light years. And the Sun is not special. Alpha Centauri, 4.25 light years away, has the same physics and very probably the same kind of shell, its own cloud of ice, its own outermost holdings reaching back this way. Whether the two actually touch is a genuinely open question that depends on where you put boundaries nobody can see. But the gap between them is not 4 light years of unowned nothing with 2 stars at either end. It is a star's territory, and then, at some point out there in the dark, another star's territory, and the seam between them is somewhere in the middle, and nobody knows exactly where. Which means there is no moment on that journey when anything is truly nowhere. There is no stretch of the crossing where a traveler could look around and say that they had left one place and not yet reached another. You go out through the Sun's furthest rooms, and at some point, without any sign or marker or change in the view, you are in the outer rooms of somewhere else. The space between the stars is not empty of belonging. It is simply divided, quietly, without a border post. I said at the beginning that we would take the friendly word apart, and we have. It is not a year, and it is not friendly. It is 9,460 trillion meters of a thing so thin it would be called a perfect vacuum, and so heavy it outweighs 70 Earths. It is the price of an impossible speed, the range at which a species stops being able to talk to itself, a road with no signs, a target that moves, and most quietly of all, a distance that is not long enough to get out of your own house. But you knew, in some way, before I said any of it. You have always known that the sky was far. What tonight was for was to find out what kind of far, and I think the answer is stranger and kinder than the frightening version. We live inside something. It is enormous. It goes out further than the unit we invented to describe the space beyond it. Nothing we build will ever cross that unit, and it does not matter tonight, because it was never a wall between us and the rest of the universe. The rest of the universe has been arriving through the window this entire time, on light from everywhere, and it has never once failed to come. The nearest star is 4.25 of those units away. And the first one of them, the whole enormous, impossible first one, is ours.